Hello everyone, I am Aswani, Assistant Professor, Department of CSA at MLR Institute of Technology. Welcome back another session of Artificial Intelligence. In this session, we are going to learn about a radial basis function network. What is radial basis function network? What is the architecture? And what are the characteristics? And we will see one XOR function in this radial basis function. Let's see the introduction part of a radial basis function network. So whichever network uses the radial basis function, then that network is called as the radial basis function network. This radial basis function network consists of three layers. One is the input layer, hidden layer, which consists of radial basis function, and another one is output layer. Basically, this radial basis function network is used in function approximation, time series prediction, regression tasks, and also control and regression tasks will use this radial basis function networks. Okay, these radial basis function networks are the type of artificial neural networks which are used for function approximation, classification, and regression tasks. Okay, what is meant by function approximation? So here the radial basis function observe the patterns and it will classify that patterns into categories. Let's see the definition. RBF networks are particularly effective for approximating complex functions. The hidden layer of RBF network uses radial basis function to transform the input into a higher dimensional feature space where the data becomes linearly separable. So here RBF will apply into the hidden layer and it will standardize the input values, then it will forward to the output. Next one is classification. So RBF networks can also be used for classification tasks. For example, email filtering, spam or not spam, disease diagnosing, disease present or not present, categories. It is used for classification. In this case, the output layer typically employs a softmax function to produce class probabilities. By training the network on the label data, it can learn to classify input patterns into different categories. The next one is regression. RBF networks can be used for regression tasks, which means continuous data. In regression, the network learns to predict continuous output values based on the input. The output layer of the network can be configured to produce continuous output values, and the network is trying to minimize the difference between prediction and the true output values. Let's see the formal definition of radial functions. RBF's functions depend on the distance from a central point called the center. For example, here there is a center point and which will if you take this as the center point, whatever values are near to this center, these will be effects more than the outer values. That is what here radial functions are. So how we can use these radial functions means they are used in various networks, single layer or multi-layer, for both linear and non-linear models also. The characteristics are monotonic response, increase and decrease in response based on the distance from the center. So what are the parameters? Center, distance scale, shape. The center, the central point of the function, distance scale, a parameter that determines how the distance is measured from the center. We can use the Euclidean distance also. Next one is a shape, defines the specific form of the radial function. Common types include Gaussian, multi-quadratic, quadric functions are used, inverse multi-quadric. So commonly used type of radial function in this case is pi of x equal to expression of minus x minus c whole square divided by sigma square standard deviation. Okay, so the architecture consists of input layer, hidden layer, and output layer. So in this input layer, each neuron in the input layer correspond to input variable. Input layer standardize the values of the input variables by subtracting the median and dividing by the interquartile range. After that, whatever values are there, that will be the standardized values are then fed into the hidden layer. After performing the some formulas, means median and dividing by the interquartile range, then that values, input values, will be fed into the hidden layer. The hidden layer contains variable number of neurons, each associated with the radial basis function. Each neuron in this layer calculates the Euclidean distance from its center point. The radial basis function is then applied to the distance. Common RBFs include Gaussian, multi-quadratic, and inverse multi-quadratic functions. So in the output layer is a linear layer that combines the output from the hidden layer to output layer. This layer produces the final output of the network. So the architecture: input layer, hidden layer, output layer, output. So in the hidden layer, which consists of the radial basis function, in this input layer the values will be standardized. That standardized values are fed into the hidden layer, and in this hidden layer it will apply the radial basis function. After performing this function, then it will fed into the output. After this output, it will add the bias, then it will produce the actual output. Okay, next, estimating the weights. To determine the weights W from hidden layer to the output layer, we can utilize the standard iterative methods of neural networks. However, due to the linear relationship for approximating function with respect to the weight, these weights can be directly calculated using matrix methods of linear least squares. Okay, so this approach eliminates the need of iterative determinations. So here the methods are linear least squares, differentiability, and output calculation. To calculate the output, the formula is y equal to f of x equal to sigma I equal to 1 to n wi pi of, means here activation function of xi minus ci plus b is the bias. So let's see the RBF neural network for XOR function. So here we have taken 2 input nodes, 2 hidden nodes, 1 output node, and producing the output. So network architecture: hidden node centers, input distance squared from center, hidden node, output pi. So the formula is activation function of x minus h1 equal to e to the power of x minus h1 whole square. Here pi of x minus h2 equal to e to the power of x minus h2, where h1 equal to 1 comma 1, h2 equal to 0 comma 0 are the values. Okay, now we can compute y value using this formula, and these are the actual tabular format. Means how it will working in a similar way. In the previous session we have seen the multi-layer feed-forward network. In the same way here also we'll compare the values by applying the radial basis function. Let's look at here. For h1 and h2 we are applying the activation functions, radial basis function. Okay, RBF network parameters. There are 3 parameters which we need to learn. The first one is center vectors, next one is weights, and the third one is RBF width or sigma. So various learning algorithm may be used to learn the RBF networks parameters. Okay. Already we have seen center, weights, and the RBF width. The algorithm here is: choose the center randomly from the training set or use clustering for determining the centers. Compute the spread sigma for the RBF function using the normalization method called d max divided by square root of n, where d max is the maximum distance between 2 centers and n is the total number of centers. So to find out the distance, we'll use the Euclidean distance method. The weights are found using the pseudo inverse method. So weight of W1 to Wn of transpose equal to inverse of pi D1 to Dm transpose. Okay, here we are assuming that there are n hidden nodes and m set of training examples with their results D1 to Dm. The matrix is defined using n Gaussian function, each for one hidden node, as follows. Here this is the formula how we can solve this one. Activation function of x1 minus c1 and so on, pi of n x1 minus cn. In the same way we will do the each and every training example. So in this session we have seen RBF network definition, working of RBF, okay. In the next session, we will see the design issues of artificial neural networks. Thank you.